Today, I thought we'd make a better hash table, or at least a more general one. Welcome back, everybody. I've talked about hash tables in the past. It's been, I think the last time I did a hash table video was 2020, and that video is definitely still relevant. It covers the basics of a hash table, what hash tables are, how they work, the basic idea, why we use them, when we use them. But the hash table that I made in that video wasn't very general purpose. It was just very specific to a particular type of data. And so I thought we would take some time today to make things a little more general, try to expand on that idea and look at how you can make data structures that you can package up into a library that then you can reuse in a lot of different projects. As is the case with most of my videos, this video will have source code, and source code is available through Patreon. Also, you can get access to my monthly office hours. So huge thanks to all of you who support the channel. But of course, the video will contain all the code. So if you don't mind typing, it's here for free. But thanks for all of you that help make this channel possible. And now, without further ado, let's jump into the code. Okay, so today I'm basically I wanted to start with the hash table example that I used back in 2020. This is the example using external chaining. Like I mentioned, that one was very focused. Like, we had a hash table that would store these person structs, so a name and an age, and we could have put other stuff in them. But I thought today we would look at making this a little bit more general so that we have a little more flexibility, basically try to create a software artifact, a data structure that you could then just drop into any project and just use it without having to change the hash table code. So this is the starting point. If this is all brand new to you, do check out the previous video and it'll help make everything make more sense. But so I've created a couple of files that we're going to use here. So hashtable.h will fill this out, and hashtable.c. So they're going in this better hash folder here, which is hopefully going to be a better hash table. I also have a make file in here. This is how we're going to build things. So you've seen my make videos hopefully before. Hopefully this isn't anything too crazy. Check out those videos if it is. But really what I'm going to do is I've just got a couple rules in here that are going to take .c files and compile them to .o files. I'm going to then create two different versions of this library. So I want to create a library called libhashtable, and I'm going to make a shared object version, and I'm going to make a static library version. I've talked a bit about these in previous videos as well. I'll link to those videos down in the description, so check them out if you're new to libraries as well. But it's just a different way to package the code so that we can use it in different projects. And so right here, you'll also notice there's a rule for compiling what's going to be my test programs. So I also have this test.c. We'll get to that in a minute. But the idea is I want to be able to take a .c file and compile it with the static version of the library, and then we can run tests on it and actually make sure that it works. And then finally, we're going to have a clean target down here that's just going to clean up everything in our project. So that's removing all of the .a files, .o files, .so files, the dsim files, which are debug files that you see if I'm ever compiling this on Mac OS. I'm working in Linux today, but I tend to leave that in there because sometimes I want to compile for my Mac. But anyway, let's jump back into here and let's take a quick look at what our interface is going to look like. So before, I had a hash function. Sure, we're going to need that, but I'm going to try to make that a little more general. I had an initialization function, so this init hash table. I also had a print table function down here. I had a hash table insert, a hash table lookup, a hash table delete, and then I had a test down here that just basically ran this whole thing through its paces. So let's try to replicate something like this. These basic functions, let's put these into our hashtable.h. I'm going to start out with, and hopefully you'll catch my errors. I'm sure anytime I make an error, you'll mention it down in the comments. But let's put some if-def guards here, hashtable.h, and then and if. Okay, this is just going to help prevent issues with like double includes and things like that. And then let's come down here and let's just add some of those same functions we had before. But because I want to make this a little more generic, I'm going to let's just type def a new data type, a struct. We'll do an underscore hash table, and then we'll call it hash table. Now, the idea here is that the user doesn't have to know what's actually stored inside of my hash table struct. This is just what you're going to be using. Anytime you want to create a hash table, you need something you can create. So this is similar to like file pointers that are returned from fopen. Same idea here. Also, I mentioned before that I want to make hash functions more general. So I'm going to also type def a type of function. So this is going to be a uint64 64t, which before I forget means I need to include standard int.h here. And then what I'm going to do here is this is going to be a hash function, is any function that takes a const character pointer and a size t. So basically telling you, here's a pointer to some bytes, and here's the number of bytes that I want you to hash. And then we're going to compute a hash and return a uint64_t. Now this should match up to close enough to this one. So this one, I was just assuming that it was a string. So I wasn't passing in a size, and I was doing an unsigned int instead of a uint64t. But other than that, basically the same thing. So we can adjust that later on to make it fit. But this is what I want to go with here. And this is going to allow me to basically change out the hash function if I want. This hash table doesn't have to be married to a particular hash function. So now let's come down and make our functions. So let's say we want a function called hash table create, and we're going to say what size we want it to be. And let's pass in, let's say you want a hash function pointer. So pointer to a hash function, we'll call it hf here. And then let's return a hash table pointer. Okay, so the idea here is this will create a new hash table with this many entries in the table, and this is the hash function we're going to use. And then it's going to return a handle, basically a pointer to this opaque struct that we're going to define inside our .c file. We'll get to that later. Then down here, we also need a way to, let's say, hash table destroy, in case you actually want to clean up this hash table. And let's pass in a hash table pointer to that, we'll call ht. And then let's also make, we had a print before, so hash table print. You notice I am trying to name things uniformly. This is really common in libraries in C. We often like to preface the name with the thing that it operates on. It makes it easier to see what belongs in what header file. We're trying to get some of the benefits that you would get from an object-oriented language here just by using careful naming. So this is going to take in a hash table. Now, of course, for really big hash tables, printing is going to get a bit disastrous, but that's okay. This will be useful for debugging in the early stages. We also want a hash table insert function, and that's I'm going to pass in a hash table ht, just like all the rest of these. And then we'll come in here and say, we need a key, right? So we're going to call this a little bit of const character key. We'll assume that your key is a string. And because we're doing this with our hash function, I'm not going to assume that it's a string. It could be, but we'll assume nothing at this point. And we'll pass in a key length. And then we're also going to pass in a void object. Okay, now why am I using void pointers? A void pointer basically can point to anything. So because I want to make this more general, what I'm going to do is have my hash table elements be void pointers. Basically, you just give me a pointer to something and I'll just put it in the hash table. And the user can keep track of what it actually is. And let's also have this return a bool, basically true if it was inserted and false if it was already there, if that key already existed. And then because I'm using bool, let's come up here and include standard bool.h. Okay, so far looks okay. Now let's also, because the whole point of our hash table is to do fast lookups, so let's make a hash table lookup function, hash table ht. So you notice all of these, I'm basically passing in the object that we're operating on. And let's pass in our key and the size t, the key length. So in this case, we're going to be looking up by key what we're looking for, and then we're going to return a void pointer. So this will grab the pointer that we stored in the hash table. Now, there is sort of an implicit rule here that I'm going by, and that is I'm assuming that you can't put a null pointer into the hash table because I'm going to return null if the lookup failed, basically if it didn't find what we're looking for. So we're gonna have to keep that in mind when we do a hash table insert, is if a null gets passed in as this argument, we're basically going to just return false and say, no, sorry, we did not add that to the table. Now, of course, you could make different decisions. You could pass back the void pointer through an argument, and then you could have a Boolean that tells you whether it found it or not. That would be totally fine as well. This is just how I'm going to do it today. And then let's copy this and make a hash table delete function. That's going to take in, again, we're just going to take in a hash table and a key length. And so it's exactly the same as hash table lookup, except because we are going to return what we found. But if we did find something, we're also going to remove that from the table. And so this seems like a good place to start. We might think of other functions that we might want to add here to operate on hash tables in the future. But for now, let's just start here. This seems like this will work fairly well. So let's take this over to our .c file. Let's include hashtable.h, and then let's start implementing some of these different functions. But before we do, let's first come up here and, oh yeah, sorry, this needs to be quotes. But let's come down here and let's define a few things. So the first thing I want to do is to create our structs. Remember, we had some opaque data types up above. So the first one I'm going to do is hash table, and let's give it a few things. Let's say it has a uint32t size. This is the number of elements, the size of the table. Let's add our hash function pointer. Just call that hash. And then I need an array of elements. So we're going to call this, we'll define this in a minute, but let's say they're entries, and we'll do an array of entry pointers. Okay, so this is just a double pointer, but it's an array of pointers. If you're new to C and not clear on the relationship between arrays and pointers, I do have a video on that I made quite a while ago. Please check that out. It'll make this a little bit clearer. But I think that's a good place to start. So we can get rid of that red line. Let's come up here and, well, actually one thing I forgot, hash table down here. But then let's come up and define our entries. We'll call this entry. And then for each entry, what I want to do is to keep track of its key. I want to keep track of the key length, because we are passing in every one of these keys, we're keeping track of the length of the keys, and then a void pointer to the actual object that we're storing. And then I'm also going to add a pointer to another entry, and that's going to be our next pointer, because I'm using external chaining. So each of these is going to be a node in a linked list. Now my size t, that's just, again, I'm missing a header file. So because I also use that up in here. I'm not sure why it wasn't complaining at me, but let's just include standard lib.h. That should take care of that. Come down here. Yep. Okay. So that took care of that. Great. So we have our hash table struct, and we have our entry struct, which is the entries in the hash table. Now we should be ready to actually start implementing things. So the first thing let's do, let's come down and let's start implementing our hash table create function. So what's going to happen when we first say, I want to create a hash table? Well, what we can do, let's actually make a hash table and malloc the size of our hash table. So that should allocate enough space for this table struct. And then we'll come down here and set the size to be equal to size, and set the hash function to be equal to hf. So as we passed in, we're basically just saving this for use later when we actually need to hash elements. And then let's allocate space for our elements. I'm going to use calloc for this because it will zero out my memory, and so it will prevent me from needing a for loop going through and setting all of those addresses, all those pointers to null. So here we'll just do size of entry pointer, and we're going to have the number of elements, if I can type today. So yeah, it's important to remember that calloc zeroes out the memory. That's one of the special things calloc does for us. So that's why I'm using it here. And then let's just return our hash table. Okay, so that's going to allocate some space for all the different pointers that we want to store to objects. And if we come down here to our init hash table, well, there's a few different things. This one's a little simpler. Notice that it does have the for loop that goes through and initializes everything to empty. But back here, we were actually using just a global hash table that I just allocated at the beginning. So in this case, we're trying to make it more general. So we're going to allocate it on the heap here, and then we'll return a pointer to it so that you could have 3 or 4 or 5 hash tables, however many you need. Okay, so let's also come down and implement our destroy function. Here what we're gonna do is, well, I'm gonna come back to what to do about individual elements. We will come back to that in just a minute, but before we do that, let's free. So once we handle the elements, then we're going to free all of our array of elements. So we're going to free all those pointers, and then we will free our hash table struct. Okay, so I'm going to come back to the freeing of the individual elements because I'm not really sure how I want to handle that. Let me think about that for just a minute. There are a few different ways we could handle that. Sorry, this video is a little more organic than usual. I haven't thought this all the way out, but we'll figure it out by the end and hopefully not make too many mistakes along the way. So for our hash table print, let's go back and kind of do what we did before, and that is have say something like start table, and then we'll have a for loop, have an index that goes from 0 to the hash table size. And then in here, let's say if the ith element is null, then maybe do we want to print out null entries? I'm not really sure. For now, let's just do it. And then as the table gets big, this is going to get really annoying, but for now, that's okay. So let's just put a tab character. I think we did this way before. Let me see really quick over here. Yeah, so we did something like this. So let's just keep that. We could just use the same thing here. So we'll print out I and say, hey, there's nothing there. So that one's empty. And then otherwise, if there is actually something here, then what I'm going to want to do is we'll do this, except now we need to go through this chain, right? We've got this external chain going on. So now we're going to do something like make a pointer, call it temp to the head of this linked list, to the ith element we know it's not null, so we know we've got at least one thing there. And then while temp is not null, we are just going to go through this and print out. Now at this point, I'm actually having some second thoughts about passing in the length of my keys. So I think what I'm going to do, I'm going to call an audible here and we're going to change things up just a little bit. But first, let's put quotes, and then we're going to print out what the actual key is that we're going to use. So I'm changing my mind. I'm going to assume that all keys are just strings. Okay, so I'm going to go up and remove the size in just a minute, the key lengths, because it's just going to make this, I think, a little cleaner. So I'm going to print out the key, and I'm going to print out the actual pointer that is stored in here. Since we don't have the other information, then I'll put a hyphen here. And yeah, so let's just print out the key, and let's print out the address of the object. And then temp equals temp arrow next to get the next note. So this is going to go just march through. And then once we're done, we're just going to printf a new line. Okay, and then one last thing we want to, down here at the very end, after our for loop, we're going to print out end table. Okay, now before I forget, I just made a fairly significant change to my design. Sorry about that. But what I'm gonna do is come up here and say, we are not storing key lengths. Instead, I'm going to assume that everything is a null terminated string. It's gonna make my life just a little simpler. This is going to force me to come up here and my hash function. Well, maybe for now I'll leave the hash function as is, but all these folks up here, I'm going to remove the key length and we'll just pass in the pointer to our string. So that'll simplify things a bit. Okay, so now we can resume. I think that's the only thing that we really changed so far. I'm sure you'll call it out if I've messed something up. Let's close up our print. Let's look at how we actually add things to our hash table. Again, let's remove the key lengths from here. We're just gonna assume that we have null terminating strings for each of these. So let's then come down here, and while I'm at it, I'm just gonna add function bodies for these functions as well. Okay, now for our insert, what we're gonna do here is we're gonna come in here and say, first of all, I'm just going to check a couple of things. So let's say if the key is null, we're not gonna allow that, right? So you can't use a null key and you can't use a null object. Okay, so either of these, I'm just going to return false, saying, sorry, couldn't add that to your table. And then finally, we actually need to do some hashing and say, okay, what is the index of this key in our table? And so I could do this. This is actually something that's going to happen in quite a few places. So let's just make a function called hash table index. And let's say hash table, and we'll pass in the key and just get the index. So let's come up here and define one more function. This is not a function that anybody else is going to be able to call. It's just a private one or static. So it'll only be visible within this translation unit. And so we'll come down here. And now what I'm going to do is say size t result equals, and let's take our hash table and we're going to call our hash function. And I really need to define these. Okay, so we're gonna call this hash function on our key. Our hash function does still require a length, so we're gonna do string length of key. Now remember that this is going to produce a uint 64_t. So I'm going to mod that to the size of our hash table. So this should give us an index into the table. It should fit from 0 to the size of the table -1, so it will always fit. And then let's just return the result. Okay, so this is just something that we'll be able to use over and over again. We'll come back down here and we need to assign that. So yeah, so we're basically going to pass in the hash table and the key, and this is going to give us the index into that table. So now what I want to do is also make sure that I don't get duplicates in my table. So what I'm going to do is say void pointer, we'll call it test, and I'm gonna call my hash table lookup function, which I haven't written yet, but I'm assuming someday it will work. So I'm gonna pass in my hash table and I'm gonna pass in my key. And actually we don't even need to save it here. We'll just say if hash table lookup key, if that is not equal to null, meaning that we actually did find something there, it's already there, then I'm going to return false. Okay, so you can't use the same key twice. If it's already in there, you got to delete it and then reinsert it. We could change this so that it overrides or whatever. It doesn't really matter, but for today, this is what I'm going to do. And then let's come down here and create a new entry for our node. So if we didn't find it, basically, then we're going to come down here and say entry E equals, let's malloc size of the thing that E points to. And then let's set the object for this element equal to obj and its key. And we're going to malloc space because I'm sort of taking the approach that I have custody over these elements in the hash table. So once you give me the key, I don't want to make any assumptions about what's going to happen to the memory that's holding that key. So rather than just storing a pointer, I'm actually going to malloc space for it. And I'm going to get the string length of the key +1. Remember, key is a string. So this will guarantee that I have enough space for that string on the heap. And then let's just string copy into our newly allocated space from the key that was passed in. Okay, so now we have our entry object, our entry struct. And so then we can come down here and insert our entry. And here we're just gonna say, we're gonna set the next pointer of our entry to be equal to the ith element, basically the head of the linked list corresponding to this hash table location. That should be index. So this is the index that we found up here. So this is the index in the hash table that we found. That's where we're gonna put it. And basically we're gonna add it to the front of the list because that's just simpler. It's gonna be faster. So we set this here and then we would say ht elements index equals E, right? So we're gonna set this to be the new head of the list. Sorry, E, and then return true because we did insert it into the list. Okay, so that's pretty straightforward. It won't work until we actually have hash table lookup implemented, but otherwise this should be fine, as long as I didn't mess anything up too bad. Okay, now let's come down to lookup. So here what I wanna do is, well, first of all, we're gonna do the exact same thing we did up top here. We're gonna add some checks and then we're gonna get the index. So we're gonna say key can't be null and let's also say hash table can't be null. I guess I didn't check that up here, but I probably should have. Now, of course, in some cases, you might want to treat the case where you passed in a null pointer as just a program error. Like this is just a bug that should just crash. And in that case, I could replace this with an assert. I'll leave that up to you to sort of do what makes most sense for your program. For today, I'll just leave it here as a runtime check. So now we have our index. What I'm going to do is come down here and we're going to get a pointer to an entry. We'll call that temp, and that's going to start at the head. So we'll go to our elements index. So that's where we're gonna start looking for this node. And then while temp is not equal to null, and as long as let's use string compare to check our keys, as long as temp's key is not the same as the key we're looking for. So string compare will return 0 if they're the same. So as long as they're not the same, then we're going to keep looking. So keep looking means temp equals temp next. And then if we get to the end and temp is null, well, then we know that we failed to find it, so let's return null. Okay, so that basically is our way of saying we couldn't find anything because we know we can't insert null into this object. Otherwise, we're going to return temp. We're going to return the void pointer to the object that temp points to. Okay, so that should work. That looks good. Now let's come down here and do delete. Now, if you remember before, delete is almost the same as lookup. We have to find as well, but we're just going to remove it if we find it. So we're going to change a couple of things. We're going to start off same thing with this check, basically making sure that we don't have null key, don't have null hash table, and we're going to get the index. And then similarly, we're going to come down here and we're going to get the beginning of the list we're going to be looking through. This time we're basically hunting through, looking for the node we want to delete. There's a bunch of different ways we could do this, but for simplicity, probably for beginning programmers, let's start with a previous pointer and we'll start that out as null. And then we're going to do this same search here. We're going to look through, basically we're looking as long as we don't run into a null pointer and as long as our keys don't match, then what we're going to do is say the previous is assigned to the temp. And I'm keeping track of the previous because I'm going to need it when it comes time to delete the node that I find, right? So other than that, it's the same. We're basically going to hunt one step at a time, but just keeping track of what the node before the node that we're looking at is. So similarly, if we don't find it here, you can just return null, but then we can come down here and we can say if previous is null. Okay, so if this case, this basically means that we are deleting the head of the list, right? So in this case, all we're gonna do is set ht elements index equal to temp next. Okay, so this basically just moves the head pointer beyond the node that we're deleting. And then otherwise it's somewhere in the middle. So in this case, then what you would say is the previous, its next pointer needs to point to the temp's next pointer. Okay, so this is just basic deleting from the linked list, from the middle. Of course, it could be the end, but anyway, deleting from somewhere that's not the head. So, and then at this point, then what we would do is we would return the object once again, so that you know this is what we deleted from the list. Now, of course, it's not quite that simple because we just removed an object from the list. So let's say something like result equals the object. And then I'm actually going to free this temp object because we don't need it anymore. So here we can come up here and then just return the result. And this is basically going to give the pointer back to the user. They can do with it what they want. So if they delete it, it comes back. I'm going to assume that they will take care of freeing it or destroying it in whatever way makes sense for them. Okay, and so now we should have a working-ish hash table that we can play with. So let's just jump in here and see if we can compile it. Okay, what do we have? Let's take a look at our warnings. There are a lot of them. So, okay, so it doesn't like that. Okay, I used string length and I did not include string.h. Okay. Looks like I also missed out on standard IO because we're going to use printf. And so now it looks like, okay, we've got the hash table being compiled to its various forms, right? You can see my .a file and my .so file are being built just as I wanted. The only issue we come into is when we get to this test.c, and that's because if we look at test.c, it's totally empty, right? There's nothing in it, so that's fine as well. So let's come in here and let's change that. Let's include our hash table.h and let's make a main function down here. Just make sure everything compiles. Okay, so now we compile. Of course, test doesn't actually test anything, but we compile. And maybe for this one, let's actually come in here and add arguments. Yeah, I think we might want to do that. Yeah, the way that I think I want to run this is I think I want to actually run this so that we can pass in. I have a couple of words lists here. So we're going to add some words to our linked list. So if argc, let's do it like this. If it's not equal to 3, oops, then let's print out a usage string. And let's pass in a word list file name right here. And then let's also, what we're gonna do, what I think I wanna do is to have it just try to a whole bunch of guesses in the hash table, guess a bunch of random words and then see what it can find. That'll be a way for us to test things. We could of course have a guess list or something like that, but let's just do something like this. It'll be interesting, maybe. And then let's return exit failure because you didn't run it right. So that's a failure. Okay, now let's open that file. So let's make file name equal to argv1 and uint32t num guesses is gonna be atol argv2. Yeah, so that one should come next. Okay, and then let's come down here and do const int table size. Okay, we're just gonna create a size for playing around with it. And let's make this, let's do something like this. This should give us a good size to work with, not so massive that we're running out of memory or anything, but you know, it gives us some room to run. And then let's go ahead and create our hash table. Just call it table. And let's call hash table create and pass in table size. And then we need a hash function, right? So this is where our hash function comes in. We need, you know, my hash function, something like that, to get passed in as a function pointer to this function. So of course we haven't created one. So let's come up and do that at this point. Actually, what I think I'm gonna do is we'll just come back here and grab the hash function that we used before. We'll just basically snag that. Since the point of this video is not to create the world's best hash function, in fact, maybe we'll take a look at that in a future video. But so over here in my test, now notice this isn't part of my library. I'm just coming in here and then we're gonna say uint64t, because that's what we were returning. And then I also needed a size t length. And then let's change this to uint64t. We can remove this because we're passing it in as an argument. And then yeah, then the rest of this should work except this. I don't need to mod it to the table size because this function doesn't know about the table size anymore. It doesn't know that there is a table or anything about the table. We're just going to return a uint64t and then we'll deal with the modding in the hash table itself. Okay, so now we should have so hash, well, we'll just leave the name as hash. I'll come down here and change this to hash. And that should make my red line go away. Okay, because now we know it. So now we're saying create a hash table with this many entries and using this hash function. Now let's come down here and open up that file. And we'll pass in the file name and we'll open it for reading. I'm also going to create a buffer we're going to read into, and let's make it something like some kind of max line. Yeah, let's come up here and define that. Let's make it something big, 4096, something way bigger than I'm ever going to need, but that's okay. Let's also come in here and keep a count of the number of words we're looking at, just so we make sure that everything worked the way we expected it. And then we'll do something like while not FEOF, well, it's not the end of file. Oh, forgot to actually name my file pointer. So we're gonna have something called FP, and we're gonna say as long as FP, it's not the end of file, and as long as F gets buffer max line FP. So that's gonna be like, we're gonna try to read in to this buffer up to this length from this file. So as long as that did not return null, then we're just going to keep reading. Now in this loop, I'm just going to read in all of the different lines in the file. Now each one, when we get a line, it's going to have a end of line character on it. So I want to take that off. That's sort of the first thing I want to do. So let's say we're going to use a function that I really have come to love for this. And that is strcspn, that's string cspan. And we pass in buffer. And then we're going to pass in a string that has a bunch of characters. And if it finds one of those characters, whichever the first one it finds, it is going to basically give us the index of that character. But if it doesn't find anything at all, it will just give us the null terminating index. So we can come in here and set that equal to 0. So that's basically just going to, if we see a /n or a /r on that line, it's going to change it to 0, which that will become the new null terminator. So it will just remove any unwanted line ending characters. Okay, now at this point, we could just say hash table insert. We're going to add it into the table. And we could here say, let's just add the key being buffer, right? Because remember, we are going to malloc space for this new thing, this new buffer that we've created. Now, the problem with that though, is that really what I want to do is just add this word to the hash table. And so like I could try something like this. Unfortunately, this is going to result in the same address, the address of this local variable buffer being added to the hash table every time. So that's probably not what I want. That's going to result in basically every single entry in my whole hash table having the same address stored in that void pointer. Yeah, I'm not really crazy about that. So instead, what I'm going to do is just let's make a new entry character pointer, and we're going to malloc space, and that's going to be the string length of buffer +1. And then we'll come down here and string copy into new entry, and we will copy in buffer. Okay, so now we can come down here and we'll just pass in new entry and new entry here. Now these don't have to be the same. In this case, I'm just making them the same because really all I want to use this hash table for is to store the keys themselves. I want to store just a big list of words in a dictionary where I can look up whether something's in the dictionary or not very quickly, because that's what hash tables are good for. But of course, this could be some other object that corresponds to this word. Just in this case, that's not what I'm doing. And then once we have inserted into the hash table, then we can come down here and say numWords plus plus. We're basically just going to count how many words we've inserted into our table. And it would be good to say numWords, not numWord. Now we can come down here and close our file. And let's print something out. We're going to say something like loaded %d words into the table, and we'll print out numWords. Oh, no underscore. Now let's just see if this worked. Let's call hash table print out table, and that should give us a good idea of whether or not we're on the right track. So let's compile this. I'm getting a warning because I'm still not using that numGuesses variable that I used up above. That's okay. We will get to that. So now we can come down and run it, and we're going to say, okay, we're going to use our words short.txt file because otherwise it's going to be massive. And let's put numGuesses as 50. It doesn't really matter. Okay, this is a bit of a problem. As I mentioned before, I had my doubts about whether we wanted to print out all of the empty entries. So let's come in and actually remove that. We'll compile it again, and let's try this again. Okay, this is actually looking pretty good. You notice we've got all of my different words in their various rows. We didn't have any collisions, which is great. And you notice that because we didn't pass in buffer here, that each of these addresses is different. So we have a different spot on the heap for each of them. So that's great. That's what we were looking for. Now you notice that we don't have any collisions right now. That's because we have a huge table and we only added 20 words to it. And so yeah, so if we add the whole file, then we are going to naturally get many more collisions. How many collisions is going to depend on the hash function, and we'll look at that maybe in a future video. This one's getting a little long already, but before we end, let's come down here first in our test and let's actually make some of these guesses. I said I was going to. So I'm actually going to take out the print because as we get lots of things going on, as we get lots of words in here, that's going to get really obnoxious. So now let's just make some guesses. Let's first just make a UN32T. I'm going to call it good guesses. And I'll start at 0. Okay. And then we are going to have a const int that's going to be our shortest guess. So we're going to, like, the shortest word we're going to guess is going to be 2, and longest guess is going to be, let's say, 15. Right? So we're going to make random guesses anywhere from 2-letter guesses to 15-letter guesses. And then let's just make a for loop here really quick, and we will just grab my parentheses, and we'll start at 0 and we'll go to num guesses. And each time through the loop, what I want to do here is basically just generate some random word, and I'm going to use the buffer that we've been using before. I've already got it laying around, so let's just use it. And then we will say like shortest guess. Now this generate random word function is one that I'm going to need to implement, but we'll start with shortest, and let's just add, so rand mod longest guess, and we probably want that to be longest guess minus shortest guess. Not that it's really critical that what the length is, but just so it matches up to what I said I was going to do. So this is going to generate a random word at some point once we're done. And then we can just in here try to look it up. So we can say if hash table lookup and pass in table and pass in this buffer that we have this random guess in. So if that is not null, so if we found it, then we're going to say good guesses plus plus. And then down here after we're done, then let's just do a print statement that just says something like %u out of %u guesses were in the table. And we'll put in good guesses and num guesses. Okay, so this is great. Now let's just go up here and come up here to the top, and let's actually go ahead and create this function, this generate random word function. And this we want to pass in something like a character pointer, we'll call it a buffer. And let's pass in a size t length, basically how long we want this thing to be. It's important that the buffer is actually big enough to hold that length, which we took care of by making it way bigger than we needed. But now we'll just have a for loop in here that we'll start with a size ti. It's going to start at 0. We'll go from 0 up to length -1. And then in this for loop, all I'm going to do is say buffer I. So the ith character in buffer is going to be equal to lowercase a plus rand mod 26 because there are 26 characters in the English alphabet. So I'm basically just going to try to get random characters from A to Z, and we'll see how many of those actually show up as words in our dictionary. Then here at the end, very last, let's just say buffer length -1 equals 0. Make sure it's null terminated. And then let's make this return void. Okay, so now we should have a working example. So let's come down here, let's compile it. Okay, that looks okay. Our warning is gone, which is nice. Now if we come in here and we rerun that, well, you notice we had 20 words and we made 50 guesses, and not surprisingly, none of them were actually guesses that were in the dictionary. So that's fine. Let's try it with a larger example. So if we go our full words file and let's say we're gonna guess something like 500,000. Right, so this took a little bit longer. You notice we loaded a lot more words into our table, and over 18,000 of our guesses actually showed up in the table, which is kind of cool. Now, there is one thing so far that we still haven't addressed, and that is, now that we're all done, we probably want to come in here. I mean, in this case, this is the end of the program, so it doesn't really matter, but let's say that this wasn't the end of the program, we were doing other things, but we were done with this hash table. Then what about hash table destroy, right? We want to clean things up. So we would call it like this, but you remember we didn't really finish hash table destroy, right? And one way that you can see we didn't finish it is if I compile this now, and let's say I run this example, but I run it through Valgrind, which is going to take a little bit longer just because, well, it's doing a lot and it's checking a lot of things. But you notice that we've got a whole bunch of memory that is definitely lost and a whole bunch that's indirectly lost. So we basically have megabytes of memory that we're just leaking. So that's not a good idea to leave in our code. So let's go back and look at the code. This video has gone pretty long, but the issue here is that we free our elements array, but we don't free the individual elements. Okay. And so I do need to come back and actually make sure I clean this all up. And unfortunately, I'm out of time for today. So this is where I'm going to stop. I hope this is useful. I hope this gives you a sense for how we could make this a little more flexible. I will follow this up with how we clean up this hash table, as well as how we drop in different hash functions and we can compare their performance. So that's coming up in a future video. If you found this helpful, make sure to like, subscribe, tell a friend, click something on your way out. And until next week, I'll see you later.